Hello everybody, this is Mike Bartles from the Hydrologic Engineering Center. This video is a recording of a webinar which took place on March 23, 2023. The presenters within this video are Greg Karlovitz, Natasha Sokolovskaya, myself, and Avital Breverman. Within this video, we describe new snowmelt modeling tools that are available within HMS. Enjoy!
Welcome to this edition of the HMS quarterly webinar. This time around, we're going to be talking about the new snowmelt methodologies in HEC-HMS that will be coming out in the next version of HMS, which is actually due for imminent release. We're getting close to winding down our development cycle on HMS version 4.11. And the cool part about this is there's going to be 3 new snow accumulation and melt methods in there, and that's going to be the first new methods for doing snow melt added to HMS since 2005. And so the team has a lot of excitement about being able to share this with everybody. I'm Greg Karlovitz. I'm the team lead for HMS, and I'm joined here by Mike Bartles, Avital Breverman, and Natasha Sokolovskaya. And they're going to present to you the 3 new snow melt methods in here. And I don't want to waste any more time. I do want to remind everybody that this meeting is being recorded. This is mostly so for the folks who couldn't join us. They have a chance to come and see all these things that we are excited about, and so that we have some nice reference material for everybody going on in the future. So with that, I'm going to turn it over to the team, and they're going to take it away.
All right, so I'll start. I'll let you guys know what we have in store for you today. First thing is to satisfy everybody's curiosity of what's in that animation. I was told it's the output from ArcStorm 2.0. And if you have any questions about that, just talk to us. So first I'll introduce the objectives, or why are we adding all this cool snowmelt stuff to HEC-HMS, other than having more chance to do tutorials and presentations, which we really like. Then I'll just talk a little bit about the background of snowmelt, not too much detail, just what kind of basic processes there are and energy inputs and outputs. And then I'll introduce the summary of the existing and new methods for the snowmelts that we have in the current and the coming versions of HEC-HMS. And then Mike will talk in more details about each of these methods and how they are, I guess, the benefits and also the pay you have to pay for those additional benefits. And then we'll have a demo of some of these methods, and Avital will talk about tech transfer materials, which I'm personally very excited about, because literally everything I know about snowmelt hydrology I learned in that advanced HEC-HMS class last week. And all of those materials and more are available to everybody, and we'll let you know where they are. And we'll also talk a little bit about the future enhancement in snowmelt. And then we hope to have some time for questions and discussion. So next slide, please. Okay, so why are we adding all these snowmelt capabilities to HEC-HMS? We are attempting to make snowmelt modeling more efficient and accurate within HEC-HMS by both improving the snowmelt methods that we already have there, but also by adding new and more advanced ones. So the one method we have had in HMS is temperature index, and it has been improved in, I guess, the last 2 releases, especially most importantly in the previous release, 4.10. It was moved from the MET model to the basin model. So that gives it more flexibility, and it allows for like spatial variation. And it's a land process, so that's where it belongs. Let's see, we've also, Oh, in this release, we added the existing method and the new methods to uncertainty analysis, which is important if you want to know what kind of effect your changes in your snowmelt parameters would have on your result. And Avital, I think, will talk about this in some detail. In addition, we added 2 brand new, more advanced snowmelt methods, the hybrid temperature index, or RTI method, and the energy balance. And we also added more and different types of outputs and some better ways to represent them. Now, while doing all this, we kept in mind the foundations of HEC-HMS, which is to allow the modeler as much power over choosing different methods as possible. So now the user can also choose their own snowmelt method, which I think is a great thing. Next slide, please. So we're on a seminar about snowmelt, so I won't belabor this too much. I think we agree that snow is important, even though I have seen 0 of it this winter in Philadelphia, but I guess the folks in the West got their share. It is very important specifically for USAs, because we are in business of managing water to provide benefits to the nation. And in addition to opportunities like hydropower and obviously water supply, it's also the snowmelt results in runoff that can be a big risk. So it is both opportunity and risk, and we must manage it effectively. Next one, please. Yeah, as you can see, a substantial portion of the United States experiences significant snowfall. And we have built our infrastructure to take care of the water, both in good ways and bad ways, and we continue to manage it with snow melt taking that into account. So it's very important to be able to model it properly. In fact, I just learned recently that the flood in March 1936, which was heavily influenced by snowmelt, caused or sped up the passing of Flood Control Act of 1936, which had a huge impact on this organization's role in flood control. Okay, maybe I went too long about the importance of snow, but next one. This slide is about what needs to happen conceptually to produce runoff from melting snow. And the bottom line is it takes energy to melt snow. So if you want to predict the magnitude and timing of runoff from snow melt with any kind of accuracy, we need to understand the inputs and outputs of the energy that goes into the snowpack. And that energy comes from several sources, which I'll talk about a little more later, but they include solar radiation, wind, air, and ground temperatures, moisture vapor condensation, and a few others. So the snow typically melts in 3 phases. First, it needs to get to the melting temperature, which is 0 degrees Celsius or 32 Fahrenheit if you must. So after that, the snow starts to melt, but it's a bit of time before any of that water becomes runoff, because the snow can absorb and hold a surprisingly large amount of liquid water in its pores. It's a porous media that has ice, air, and water in it, and the amount that can be held before any kind of runoff happens typically varies between 3 and 8%, but can even go up to 15% for particularly slushy snow. And that period is called ripening. And then after that, once the snowpack is saturated, any further energy applied to it would result in water leaving the snowpack and becoming runoff. If we want to model the snow, we should represent all three of these phases. So next slide, please. So this is the equation representing all the different, well, I guess the main sources of energy inputs and outputs to Snowpack. We like to show these equations because when we go on to talk about the different methods, we talk about different simplifications and which of these terms are omitted for each method. Kind of similar to what we do when we discuss like Saint-Venant's equations for routing. First you go into the full mode and then you simplify for different methods. So in general, the largest contributors to melting a snowpack are the first two terms, which are radiative forcing, a short wave and long wave radiation. And they're shown in red also. The short wave radiation comes from the sun. And not to go into too much detail, which I don't know anyway, that's where the albedo comes in. And that's a cool word to say, albedo. So albedo is the ratio of how much of that shortwave radiation is reflected from the snow versus the total shortwave radiation. And in simple words, the higher the albedo, the more radiation is reflected and less is absorbed. So as the snow ages, its albedo generally decreases and it becomes easier to melt the snow. And then the other terms have to do with the temperature, mostly have to do with the temperature, the next two terms, the sensible heat flux and the latent heat flux. The later has to do with change in state. So like if you have rain and snow event, you'll have snow melting faster because the vapor, like there's high, what's the word? High water vapor concentration in the air, and that will condense, and that releases energy. So even though you could have the same temperature, the snow will melt faster if there is a high humidity. And then the last two terms are the heat from the rain itself and from the ground. Okay, next one, please. So this is just the summary of all the snow modeling methods that we have in HEC-HMS as of version 4.11. The first one is the simplest. It's a temperature index. It has been in HEC since 2005. And when I hear 2005, it does not sound as that long ago to me. It's like it's this century, but it is almost 20 years. So we are ready to get some updated stuff into the software. So the temperature index method is very simplified, but very useful, and it uses temperature as the only source, like as the only surrogate for energy input into the snowpack. We have both banded and gridded implementation in HMS. The second method is a new addition. It will be released in 4.11, or I guess you already can use it in the beta versions. And it's RTI, Radiation Derived Temperature Index, or also a hybrid method. It fills the gap between the simplified temperature index method and the involved complex energy budget method. And it does account for some of these additional energy inputs to the snowpack, but not all of them. It incorporates some topographic, cloud cover, vegetation, and albedo effects. We do have it as gridded, but no banded. And then finally, the energy budget is another new method. And it explicitly accounts for all the energy inputs to the snowpack. And it also requires most meteorologic inputs. And that one has both banded and gridded implementation. Next one, please. So this is just the cartoons to summarize what I presented before. Which of the energy inputs from that long equation are we using in each of the methods? So for the temperature index method, the only one that really makes it into consideration is the long wave, and it's not even directly accounted for. It's the temperature is a proxy for that. And then next, in the RTI, both long wave and short wave radiation are accounted for. And Mike will talk more about this as well. And then finally, in the energy balance, every single one of those terms is accounted. Okay, next. For the temperature index, the only boundary conditions it ever needs is precipitation and temperature. And then the hybrid needs quite a few of them. And then for energy budget, you need every single one of them. And with this, I'll pass it to Mike.
Sweet. Thank you, Natasha. I appreciate it. And thank you guys for jumping on to the WebEx today. I always enjoy talking about snowmelt with anyone and everyone who's interested in it. Natasha was correct. We have received a significant amount of snowpack or snowfall this year in the West, kind of record-setting. But that's not always the case. And we also want to represent the complexities that the entire nation offers in terms of different situations involving snow. I grew up on the East Coast. We had shallow ephemeral snowpacks there. We could accumulate and melt snow 5 times in a winter. Here in the West, it generally accumulates and accumulates and accumulates and accumulates and then eventually melts afterwards. We want to offer these methods to everyone to be flexible across the board. As Natasha mentioned earlier, you get to choose, right? In the past, you get to choose one method, one snowmelt method for the entire modeling domain, which was within the meteorologic model. But now that we've moved that to the basin model, you can choose which snowmelt method you would like to use for each individual subbasin, right? So keep that in mind as I describe some of these methods. Some of them are more complicated than others. Just because they're in there doesn't mean that you have to use them. You get to choose within HMS, which is a really powerful thing. A little bit of background on the temperature index method. It originally came from the stream flow synthesis and reservoir regulation model, which the Corps of Engineers was using back in the 80s, which in itself was derived from the snow hydrology work that was originally published in 1956. If you guys haven't read this report, the Snow Hydrology in 1956, check that one out. That's a seminal tome of information. It's like about this thick, full of really, really good detail on the evolution of snowpacks themselves, but also how can we represent that in a couple different ways. And that's where we owe temperature index to. It came from that. Temperature index, though it seems simple, has really been used widely throughout the entire world to represent the accumulation melt of snow. We only have the ability to represent energy inputs with one term, the temperature, air temperature itself, but we can do some cool stuff with the melt rate to allow that to change throughout time, throughout a simulation. So you can start with an initially low melt rate for newly fallen snow that may have a very high albedo and reflects a lot of energy back into the atmosphere. But that changes over time as the snowpack ages, grain sizes change, it may get darker in color and absorbs more energy, right? So the melt rate can increase. You can also modify the melt rate during times of rain when you do have moisture condensing from a vapor onto the snowpack. So we can do all sorts of cool things with the melt rate and temperature index. You can also have a constant melt rate, right, to represent those shallow ephemeral snowpacks that I was used to growing up. I like to present pros and cons on these methods as well. So let's talk about those a little bit, give you a couple advantages and disadvantages. First, the temperature index method, really mature. It's been around for a long time, much longer than me. It's been used on thousands and thousands of studies throughout the US. We've spent billions of dollars, if not trillions of dollars, in infrastructure decisions using this method. It's easy to set up and use. It only requires limited boundary conditions, which is really one of its strongest things, right? It only requires precip and air temperature. While there are a few parameters that you do have to specify, there aren't a ton of them compared to other snow methods, so we can consider it parsimonious in that only a few parameters are truly controlling of the actual accumulation and melt and evolution of the snowpack itself. But some of the disadvantages, it may be too simple for certain situations, right? We're going to talk about some of those situations here in a second. There's also limited amounts of output that we can supply with that. Things that are specifically missing, stuff like albedo or snow depth, we don't actually compute that within the temperature index method. So you can't actually get those. Now let's get at some of the improvements that have been made. We call these two things the same, essentially. The hybrid snow method, which you'll see in the actual HMS user interface, it's essentially synonymous with the radiation-derived temperature index method that Mike Fulham, who's also in the audience, it's good to see you, Mike, came up with and originally published in his 2015 paper. This method improves upon the temperature index method by using essentially a proxy temperature. And we can get at a proxy temperature by including representations of long and shortwave radiation. Since we do that, since we incorporate short and long wave radiation, we can do some really cool things, like account for solar shading, right? Look at this picture on the right. Where's the snow in this area? It's where the sun doesn't shine all the time, right? Snow is going to do that, and we can represent that with solar shading processes. You can't do that with temperature index. And I'll talk about how we actually go about doing that in a second. You are required to add or supply at least some additional meteorologic boundary conditions. We've further separated a few of these things as well that used to be ingrained within the actual basin model computations into their own meteorologic methods, allow them to be used elsewhere. It is also a relatively new method, so keep that in mind. All right, first things first, we start with the air temperature, right? That's a boundary condition that we got to supply. You're used to supplying that if you've done temperature index before, but so it goes. We also supply long wave radiation and short wave radiation, or at least simplified methods to estimate those two. Given those two boundary conditions, those two additional inputs, we can come up with a proxy or pseudo temperature. A radiation temperature is what we call here. So note the scales on the upper left plot, the air temperature plot, and the lower right plot for radiation temperature. They're very different. The highs are much higher for radiation temperature and the lows are much lower. Those are the times when the sun is shining or not shining on the snowpack, right? Once we figure out this temperature, which is a better proxy for energy inputs to the snowpack, the melt computations proceed relatively similarly to the temperature index method. So not a whole lot different after that point. There are some additional cool things that we can do with it, but if you're used to temperature index after that point, you'd be used to this one too. To get at those additional capabilities, we got to do a couple things to the terrain beforehand. So we specifically have to pre-process the terrain for slope and aspect and solar shading to enjoy these additional capabilities, right? Just a warning, solar shading computations are somewhat expensive. For reference of what we're actually doing, we got to search throughout the entire raster for every single grid cell. We got to see, is that being covered by some topographic effect for every hour of the day for every 10 Julian days. So the bigger the raster, the more we got to process. The finer resolution the raster, the more we got to process, the more time it's going to take. But this only needs to be done once. You pre-process this raster, your terrain raster, one time, and you can use it for a billion-year simulation if you want to. You don't have to redo it over and over and over again. You don't have to do it every time you make a forecast either. You just do it one time up front, and then they're ready to go. You access these options by right-clicking on the terrain dataset and selecting the pre-processed slope and aspect and solar shading options. In the future, we'll make that a little bit better and allow for different ways to pre-process these rasters as opposed to a right-click option, and we'll also speed those up, I promise. All right, back to the pros and cons. Really powerful thing about the hybrid or the RTI method, we can incorporate cool stuff like short and long wave radiation. Because we do that, now we get to get the additional factors of topographic shading, right? We also get additional outputs, which is really powerful. Things like albedo, we can actually output as part of this, this method. You are required to supply these additional meteorologic boundary conditions. We got to figure out how incoming solar radiation from the sun impacts or interacts with the atmosphere. So you got to supply additional meteorologic boundary conditions to do that. We do approximate a lot of things for you, or have methods for you to approximate them, but you will have to do that. And it's also less mature than newer methods. All right, now let's talk about the whole shebang, the energy budget method. This is originally based upon the energy budget method from David Tarbotten, originally published this in 1995. If you're used to the energy budget method from HEC-1, it is not the same thing. It's a brand new set of computations. What's going on is we balance the energy flux and the mass flux within a single snow layer and also balanced with the upper part of the soil. You get to specify that. So think of that volume as a control volume, and we're figuring out what goes on, or what goes into, what comes out of, and what's stored within the control volume. A change in energy content is going to affect the snow water equivalent of the snowpack itself. Just keep that in mind. We require a lot of additional boundary conditions to take care of that. So that equation that Tasha showed earlier, everything you got to supply is boundary condition. We do have some buffs coming to them, so you don't have to have pre-computed grids of, say, relative humidity, for the 1950s if you want to use this thing or this method. We'll have some additional ways to go about that. The image that I show on the right-hand side is from the January 1996 flood at Harrisburg, Pennsylvania, on the Susquehanna River. There was a lot of precip that fell, a lot of high temperatures, but also a lot of wind that was occurring during that specific time period. That wind was actually adding energy to the snowpack, right? We have mixtures going on here and a lot of precipitation falling onto the snowpack. It's not the energy from the rain per se, it's the energy from the wet, humid air that is causing the snow to melt very, very quickly. You may be able to do a better job with those situations with the energy budget method. I just want to impart on you really quickly what's going on internal to those computations within the energy budget method, because we got to iterate to solve some of these things. We essentially have more unknowns than we do equations, so we got to do some fancy schmancy math to figure that out. We have an outer loop. The first is going to compute energy and mass flux for a specific time step. What's a good guess for energy budget, or for the energy and mass flux? What happened previously is a pretty good guess. So we'll start with that. But to actually compute that energy and mass flux and also the state of the snowpack, we also have to guess and check on what the surface temperature is, and that requires iteration. So inner loop B requires up to 10 or 15 iterations. Outer loop A requires also 10 or 15 iterations. All I'm trying to impart upon you is that this is computationally expensive, can be computationally expensive, right? Also, the computations aren't guaranteed to converge every single time step, but we do try really, really hard to keep the car from driving off the cliff on this one. We'll bring you back if it does start to fail, or at least let you know why it's failing. Let me know if you find a situation where that doesn't actually work, and I'll do what I can to make that happen. This will take longer to solve than the temperature index or RTI methods, just by its very nature. Imagine doing this for every single grid cell. You can start to see that the time starts to add up a little bit. But the really powerful thing about energy budget, you get the whole kit and caboodle. Every single way that we typically estimate radiation or energy inputs to a snowpack, we can represent them in this method. We also get all those bangs from the RTI method as well, like incorporating solar shading, all that cool stuff there too. You can do the same thing with energy budget. We also output awesome outputs. Things that are really powerful, like snow depth, right? If you've done any snow hydrology in the past, you know that there's a lot more observed snow depth information to be had than snow water equivalent. You can directly compare outputs from the energy budget method to those observations. You don't have to convert to SWE. We do that internal to the computations, right? But you may not have that for your observed data. So now you start to compare apples to apples there. You have to pay the piper with the additional meteorologic boundary conditions, and also the computations are a bit more intensive. These things are not as well known, the inputs are not as well known, people aren't as familiar with them, so I'm going to consider this a much less parsimonious method as well. All right, I'll kick it over to Avital for a short demo.
Okay, so I'm going to demo some of the features that Mike and Natasha talked about. I'm going to show two HMS models. The first shows a point or lumped implementation of the snowmelt models, and the second will show a gridded one. So this is the Swamp Angel study plot located in southwestern Colorado. We've represented the plot by a single subbasin element here, not particularly exciting, but this is just to show you that the point-based versions compute relatively quickly in just a few seconds. And I'll talk about why that's important later when I talk about calibration techniques. So you can access the snowmelt parameters in a couple of different ways. If you select a subbasin element, you'll see in the component editor that there's a snow method drop-down menu. And prior to version 4.11, we only had temperature index and gridded temperature index. We now have 3 additional methods. If you select any method other than none, you'll get this snow tab where you can enter snowmelt parameters for each subbasin separately. You can also enter parameters for all subbasins at once by accessing the global editors here. So I only have one subbasin, so you only see one row, but if I had 100 subbasins, you'd have 100 rows, and you could change parameters all at once. This is really nice because it also sticks, like Natasha said, to the foundations of HMS, where we allow you to select different methods as well. In one model, you can select different snowmelt methods for different subbasins and develop different parameterization. So you can also view results in a couple of different ways. We still have the right-click option. So we have this nice snowmelt graph where you see precipitation depth, air temperature, and SWE. Black line is observed and the blue is simulated. You can also view results from the Results tab, just like with any other simulation. So like Mike talked about, there's a number of time series that are outputted that are of interest. So in addition to the usual, I'm going to actually show energy budget. So we have Snowpack energy and temperature. You can see your inputs like the radiation time series. So I talked about observed SWE. You can link a reference observed SWE time series using the option tab in the component editor. And in this case, I had a SNOTEL station located close to my study plot. And so I've referenced it here as a time series. I'm now going to switch over to the gridded model. So this is of the Upper Truckee River in Northern California. And this subbasin is just a single subbasin located directly upstream of Lake Tahoe. So the Truckee here flows northeast into the lake. And it's a gridded modeling domain. So you can still view all the time series results as you did with the point-based model, but you can also view spatial results. So I'm going to select a simulation that I've already pre-computed. And as you can imagine, this takes a little bit longer than the point-based version because the computations are performed on a grid cell by grid cell basis. But we have this really nice scroll bar, so you can scroll through time and see your results. So for this particular water year, we had peak SWE in late April. So I'll just show you that one timestamp. If I hover over a grid cell, you can see the output that you chose. So in this case, it's SWE. So down here further, closer to Lake Tahoe, we have about 27 inches of SWE. And as you move further up in elevation, we have more. You can see a lot of different output time series. So I'm going to select albedo because I think this one's really interesting. And you can see how that reflectivity varies in time and within the single subbasin. So in addition to linking something like a SNOTEL station or an on-the-ground SWE station observation, we're often working in watersheds where we want SWE we want to calibrate to SWE throughout the modeling domain. And if you're not in one of the few Western states that has SNOTEL stations, or if you don't have a snow course nearby, you might be using off-the-shelf gridded products to calibrate for SWE. So a couple of the common ones that we use are SNODAS, the Snow Data Assimilation System, and the University of Arizona SWE data set. And what you can do is extract a subbasin average time series of SWE and then reference it here in this options tab. So many of you might have used the Vortex suite of utilities, which are now built into HMS and can be accessed from the tools data menu. And the one utility that I'll highlight is grid to point. So what you'll do is open this dialog box. You'll select a grid cell. I'm not going to actually walk through the process. We do have tutorials about this, but you'll select a grid cell and select your grids and your variable of interest. So in this case, it would be SWE. And then you can clip the grid to a subbasin, which you can export out of HMS. That time series will get placed in a DSS file that you can then reference here in the options tab. So I talked a little bit about the runtimes between point and gridded modeling domains. So we're often using a point model to get a model up and running. We're calibrating to SWE depth at a point location, but we generally don't care about depth at a location as much as we do about volumes. And so those point-based models can be used to develop initial parameterization and speed up your calibration time, and can then be applied to a larger gridded modeling domain such as this one. I'm going to switch back over to PowerPoint. All right, so the snowmelt parameters are available within the optimization trials, and for all three methods. If you have observed SWE data, like I just showed, that you can actually automatically adjust a combination of parameters to develop a best fit combination. But I want to stress that the optimization trials are not designed to be used as automated calibration. The purpose is for you to spend time manually calibrating, adjusting parameters to a reasonable range, and investigating the impact that those parameter values have on the results, and then coming in with an optimization trial to fine-tune the parameter ranges. So right now in the optimization trials, you can optimize any constant value parameter, either using a gridded or banded snowmelt approach. We don't yet have the functionality for annual patterns or functions. So here I'm showing the results of an optimization trial. We selected 3 energy budget parameters, and we have an initial value for the albedo decay coefficient of 400 hours. And as you can see, the trial converged in a couple hundred evaluations at a value around 310. But this trial would take many more evaluations if you had a much larger range of values, or if your initial value was nowhere near your final optimized value. So keep that in mind when you use this, that it is not automated calibration. All of these snowmelt parameters are also available within the uncertainty analysis, and this analysis is great because you can use it both to inform calibration as well as to investigate uncertainty in parameters even after you've calibrated them. So the point of using an uncertainty analysis with a snowmelt model is to investigate how much uncertainty in an output is attributed to snowmelt parameters. So that output might be SWE, flow, volume, or reservoir elevation. And just like the optimization trial, you can use both gridded and banded approaches to all the snowmelt models, but only constant parameters are currently supported. We are working on adding the capability to evaluate uncertainty in annual patterns or functions. So here we're showing the results from an uncertainty analysis for Margus Creek Dam, which is located in the Truckee River watershed in Northern California. And we have held all parameters constant with the exception of the wet melt rate. We're also using January 1997 meteorology, so precipitation and temperature here. And what we've done is vary the wet melt rate uniformly between 0.05 and 0.2 inches per degrees Fahrenheit day. And then that random sample is applied, the same value is applied to all subbasins. So what you see here is that even after calibrating the other parameters, there's still a significant amount of uncertainty attributed to one parameter. And this uncertainty needs to be propagated and incorporated into the reservoir regulation manual and design decisions. So we have a couple of new tutorials that have been added to the modeling snowmelt section. 2 of them focus on calibrating. So I showed the 2 models from those. One is focused on calibrating a lumped or banded model. That's using the Swamp Angel study plot in Colorado. And the second is using gridded implementations of these snowmelt models, and that's the Upper Truckee River one. So each of those tutorials steps through all 3 snowmelt methods, so temperature index, RTI, and energy budget. We also have a tutorial dedicated to applying the temperature index snowmelt method for dam safety studies, which has been historically used. And we've started adding a new set of tutorials dedicated to evaluating snowmelt parameter sensitivity. So I'm going to talk a little bit more about those parameter sensitivity tutorials. The figures you're seeing here are what we refer to as tornado plots, and they were generated using multiple linear regression in Excel. And these plots are used to evaluate the relative contribution of each parameter to some output of interest. So in this case, we selected peak SWE. The magnitude of the bar shows the relative contribution of each parameter to peak SWE. So the left plot shows the gridded hybrid or the RTI parameters, and the right plot shows energy budget. The largest bar, so on the left plot, base temperature has the largest positive sign, and that sign indicates the direction of change. So as you increase base temperature, your peak SWE also increases. The melt factor down on the bottom of the left plot has the largest negative magnitude, and so as you increase melt factor, your peak SWE decreases. So these plots, this uncertainty analysis gives users a sense of which parameters are most impactful when you're calibrating. So the plots were generated specifically for Swamp Angel study plot, and we were specifically looking at peak SWE, and so the results will change depending on your watershed and what your output time series of interest is. But in this case, if I was using RTI or hybrid, I would want to focus on calibrating parameters like base temperature, the melt factor, and the maximum negative melt factor, and I'd probably spend less time on something like the wind function, which has very little impact on the results. We've also updated the user's manual, so there's now information on required meteorologic model components and parameterization. And we've also provided links to relevant journal and other papers for additional technical information. We just taught the advanced HMS prospect class last week for the first time, I think 4 years. And so the snowmelt modeling lectures were updated to reflect all the new models that are now available in 4.11. A number of the slides that we use today in this webinar came from that class. And so if you're interested in learning more, you can check those 2 lectures out. There's additional information on parameterization, calibration techniques, optimization, and uncertainty. And all the tutorials and this class material are available on our website. Now I'm going to pass it back to Mike to wrap up.
Excellent. Thank you, Avital. This is a part in the presentation where we talk about where we are heading in the future. One of the big goals, to revisit what Natasha had said earlier, was to enable users to select the appropriate modeling methods when necessary and where necessary, right? We want to continue down that road by also allowing you to select some more complicated things when they're necessary, such as frozen ground, right? If the winter was particularly wet, or the fall was particularly wet, and the winter was really cold, that water can actually freeze in the ground and take up pore spaces and actually change the structure of the soil itself too, to essentially limit the amount of water that can infiltrate into the ground. We would like to allow you to use simple, more complicated methods to go along with all the other choices that are available within HMS as well. The additional albedo methods are also something of interest that has a direct role to play in post-fire changes to the accumulation and melt of snow. Think of all the black carbon that comes off of burnt trees and other vegetation and stuff like that. That changes the albedo of the actual snow itself. It'll absorb more radiation. It'll behave a whole lot different than it did before melt. We also want to make things more accessible, right? We want to explain the new methods a whole lot better, so that's the reason for the additional tech transfer materials. So continue adding explanation and applications, but also make meteorologic methods easier to parameterize or set up and use, make gridded methods more easy to parameterize and use, and also use more data. So the implementation of the MetSim or the MT-CLIM climb disaggregation techniques are meant to take daily average data. Think of daily accumulations of precipitation or daily average temperature or min and max temperature, and disaggregate them down to sub-daily, right? Because those are very common things that we can use in the future for forecasting scenarios or other climate change applications. We want to also use that in a realistic sense if we want to run it like a 15-minute or an hour time step and do a better job of just averages. All right, next slide. All right. I want to give a major shout out to all the partners that worked with us on implementing these new techniques, these new methods, all this documentation as well. Major shout out to Angela Dern and her crew in the Northwestern Division Columbia River office. They've been instrumental in supporting this from day one. The Arid Regions Work Unit is set up by Ian Floyd and Travis Dahl. You guys have been majorly supportive. Major thanks to you as well. The Mississippi River Geomorphology and Potamology program that's led out of the Mississippi Valley Division, they were majorly supportive of all the new meteorologic capabilities in there. So you have them to thank for enabling us to add that capability. And also the USACE Agency, the Science and Engineering Technology program, the SET program. They're there to help for documentation purposes. All the new webinars, all the tech transfer stuff that we come out with, they're majorly supportive of that. We wouldn't have been able to add this stuff without you guys. Major thanks and shout out to them as well. All right, one more slide. Does anybody know where this picture was taken from? Send me an email, send me a text, whatever. I'd love to hear about it. It looked like a Dr. Seuss kind of thing. I've never seen trees hold this much snow before. Usually we're like, the canopy doesn't particularly matter. Canopy really matters in this case. So interesting picture here. If you're interested in more information, you want to download the beta, you want to use version 4.11, please hit up our website. Get your link there at the bottom. If you're interested in staying in touch with us and being added to the email list, send us an email on that email list as well. There's a link that's pasted at the bottom. We keep people up to date on software releases, upcoming webinars, everything else like that. I'd love to hear from everyone. Now, I'd like to kick it over for some questions.
Yeah, we've had a couple roll in. Yeah, what I was going to do, we've had a couple of open ones here at the very end. We've tried to tackle a few, and I'll go over those in just a second. But Mike, could you comment a little bit? We've got two questions on data products available to support the new methods, and then we had a second question that was specifically about short and long wave radiation.
All right, I see him coming in. I haven't looked at that one in a second. Data products. Can you remind me of that one?
Yeah, question says, can y'all speak to data products available to support the new methods?
Okay. Yeah, so that is a good question. The reason the energy budget snowmelt hasn't been used, everywhere, especially for historical events, is because we don't have a lot of that information, right? very cool thing that Mike Fulham did as part of the RTI implementation was come up with simplified methods to estimate those required boundary conditions. They're not the same as actual observations, but we can do a pretty good job estimating the amount of incoming solar radiation to the top of the atmosphere, at least based upon where you are in the world, what the time of day it is, and what the day of the year it is, right? We know where the sun is relative to the earth, or the earth is relative to the sun. We can figure out how much radiation is coming into the top of the atmosphere. Then we got to do a decent job of estimating how much of that radiation is dissipated or bounced off of things as it comes down through the atmosphere. Therein lies some of the simplified methodologies, right? Those things are coming online soon. You will be able to use simplified methodologies to estimate these variables. Another common application is we might have GCM output that may or may not be downscaled. Precip and temperature typically is, so you can directly incorporate those within your simulations. You may want to disaggregate in time, thus the need for MetSim methodology that I mentioned there before. But given those inputs, we should be able to estimate others as well. Like we can do a precipitation-based relative humidity estimation as well. So there are some things we're trying to fill in, some gaps we're trying to fill in there. If you're interested in more information on that, definitely hit me up, send me an email. We'll talk through that.
I just want to mention that Natasha put a link to the snow data sources component of the advanced HMS class in the chat as well. I'd highly recommend browsing some of that material from the advanced HMS class because we went over quite a bit of the application of this stuff. So snow data sources are really useful to look at there.
Yes.
We had another question a little bit previously. There was a question about the plots available that Avital was showing for all melt methods, just the new ones. And I wanted to clarify real quick that those were generated external to HMS, those tornado plots. Those are something that we want to add in the future. So if you're somebody who's using the uncertainty analysis quite a bit in your day-to-day work and you want to partner with us to figure out how to get those in there, please reach out to us. Those have kind of been on our radar for a little while. We need a partner to help fund us to get those across the finish line for that. So let us know if you have an idea for that. Let's see here. We had a question about the guides online, the specific tutorials that were shown here in the slides, and Avital provided the modeling snowmelt tutorials. There's also a couple that I think are still under construction and aren't available to public view yet, and so those will be coming online here shortly. We did have a question, and Mike took a stab, or kind of, I do want him to kind of substantiate this one a little bit because it's a really good discussion. The question was, is there a recommended grid size to optimize compute time and still get sufficient resolution for solar shading? And Mike, if you want to elaborate on kind of the situation with that a little bit for everybody, that'd be good.
It's very similar to what is the best terrain resolution to delineate a subbasin, right? It's along the same lines. You got to pay for that extra resolution, right? It may be slightly more accurate, but it may not turn out the best for you in terms of the amount of time you got to spend processing that. We don't have a great answer. But for terrain, we do. We have a really good answer for that, and we have a lot of really good tools for your use to do that. Specifically, a nice one that Matt Fleming wrote. If you haven't seen it yet, check out our tutorials and guides page on using the coarse resolution terrain data to get improved accuracy. But we don't really have a good answer for resolution for solar shading. We would like to investigate. It's going to depend upon the nature of the terrain. Specifically, steeper slopes may be behaving differently than flatter slopes. In the Great Plains, right, you're not going to have a whole bunch of topographic shading. So maybe you can get away with really big grid cells, and that doesn't really matter. But in constantly varying terrain, you may have to go finer resolution. It's also going to depend upon your study purposes. Do you truly need crazy amounts of accuracy on solar shading? Then you might want to go smaller. The good news is we allow you to change that thing subbasin by subbasin too, right? So you can go from 10-meter horizontal resolution all the way up to 1,000 or 10,000 meter horizontal resolution for your discretizations. Use the structured discretization, which lets you do that. So you can go from very, very fine to very, very coarse, but I would like to investigate this in the future. If you're interested, hit me up. Let's talk about it.
Yeah, it's one of those where being on the cutting edge makes it a little bit hard to have actionable guidance all the time. And right now we're kind of in the situation where the tools are advancing and we get a chance to actually play with them a little bit now that they're in the software. So answering those questions, hopefully we'll be able to get in a little more detail on that. We had a request for the PDF copies of the Tarbot 95 and the Fulham 2015 papers, and Avital placed a link to those. Basically, they're the user's manual section on snowmelt in the chat. So if you are curious about those journal papers, the basis for these methods, those are available. Let me see here. We had a question early on. It's not specifically related to snowmelt, but to HMS more generally. Is there an estimated release time for HMS 4.11? Right now, our lead developer indicated in the chat that right now we're targeting summer of this year. One note about our beta versions as they come out, they're fairly substantially complete when they come out. We're at a point right now where HMS 4.11 is feature complete. And we're working right now on winding down on things like repairing bugs that we've discovered with our testing and things like that. So if you go and you grab a beta version of HMS, it's in a place where the software is really stable and easy and a good place to use. And all the features are in place, including all of these snowmelt methods. So if you do want to try them out, go ahead and get the beta version of HMS 4.11. And if you do encounter anything that any trouble with it, if it's bugs or other difficulties in using the software, let us know, especially if they're bugs, because we want to try to get those fixed prior to the release, which we're shooting for this summer. Another question from Melissa: would HMS implode if you had a grid of varying size, less resolution in flat areas and more resolution in steep areas? And the kind of comment on that is, I think RAS does something like this.
And just answer that one. So
Yeah.
the grids themselves cannot change in size, right? So you get one and only one shot at resolution, lower left corner, extents that can't change. The discretization of the subbasins, though, can change. Every single subbasin can have its own discretization. So you can go from very, very fine scale where you need it to very coarse where you don't need it. And certain MET methods that we have in play will compute radiative forcings or your boundary conditions for each grid cell. So you can go very, very fine scale where needed to very, very coarse where you don't need it. You cannot put different grids with different resolutions, like layer cake different grids of radiative forcings into HMS. That's a nightmare of trying to do that. But there are ways to get around this problem. First things first, though, is figure out where it's important before we send you down the rabbit trail of like you want to always do this. Hit me up and let's talk about when and where it's important. We can actually do some sensitivity testing on that. I would like to know myself.
Let's see here. As of right now, I'm not seeing any other questions in the chat. Mike, Avital, or Natasha, if there's any other kind of final parting thoughts you wanted to share with anybody, we've still got a little bit of time.
I am very thankful that everybody, there were like 150 people who showed up to talk about snowmelt or learn about snowmelt. Thank you. Can't even tell you how excited that makes me, right? Because this is a very important topic and one that really hasn't been updated in a very long time within HMS, right? In 2005, I was in high school, so it's really nice to add new capabilities to HMS and make it better, bringing it up to speed with some of the other modeling choices that you have within HMS. So very, very thankful for everybody showing up, asking great questions. Let us know if you have any additional questions, and we'll do our best to answer them in a timely manner. We will edit this video. We'll post it up to our website soon. So anybody that did miss it can check it out and view it after the fact, or if you want to watch it again, feel free to do that too. Avital, Natasha, you guys have any?
There's a question, I think, about Sacramento River, or did you? Okay.
The two models that I demoed, if you go to the modeling snowmelt tutorials link that I provided a little further up in the chat, you can download both the beginning models for the tutorials and then the finished calibrated version. So they are on our website.
For the demo, they are both available. If you're asking about like that huge Sacramento River model that we demoed in the first, or we showed in that slide in the first, hit me up and I'll point you in the right direction for that one.